All right, welcome everyone. This lecture today, we're going to finish up where we left off with the first video that was posted this week, which was on the lives and deaths of stars. We talked about how stars were formed. We talked about sun-sized stars, how they're going to die. They're going to give off a planetary nebula and leave a white dwarf star behind at which was the center of the star. And then we finished up by talking about very large stars and what happens to them at the very end of their lives. And more massive stars don't die quietly with a planetary nebula, they die with a bang, with a supernova explosion. And after a supernova explosion, a natural question might be, well, is anything left? And the answer is sometimes, yes. There's usually something left when stars that are more massive than our sun, the range is maybe 4 to 8 times more massive than our sun, when they explode in a supernova explosion, the outer layers are blown away, but what's left behind is a very small, incredibly dense core that continues to collapse. Gravity presses that material in on itself so tightly that the protons and electrons, the positive protons and the negative electrons, they actually combine together. And when you have a positive charge and a negative charge, you combine them together, they cancel each other out. And what you're left with is a neutral charge. And we have a giant ball of compressed neutrons. So this makes sense. Astronomers aren't super creative. We name the star a neutron star for that reason. So the two main components, the two biggest things that we know, the main properties of a neutron star, are that it's incredibly dense and it spins really fast. So for the dense part, neutron stars they have a lot of mass. But they pack it into a really small amount. So more than you can see in the picture on the right there's 1.4 solar masses, so more mass than there is in the entire sun, almost 1.5 solar masses. But the size that it's packed into is really, really small. This is a picture over a part of New York, or I think it's over Manhattan, that would show the comparison between the size of the neutron star next to Manhattan. So you can see it's as small as a city, but as massive as the sun. So they're so dense that if you are able to go up to a neutron star, stand on it, which you wouldn't be able to because the gravity would be so good. Our bodies could not withstand that gravity. If we stood on a neutron star, we'd instantly be smashed into a smear of people jelly, which is about 1 atom thick on the surface. But if you were able to go up and take a teaspoonful of a neutron star, well, you wouldn't be able to lift it because it would weigh about 1 billion tons. So on average, the gravity on a neutron star is about 2 billion times stronger than the gravity on Earth, just because it's so dense and it's so small that you're so close to the center that gravitational pull is going to be an incredible amount. So the density is one of the main characteristics, and that's usually what you're talking about when you're referring to neutron stars, just that significant amount of density. But the other property that they have comes from the power of that supernova explosion. It gives the star a really, really quick rotation, causing it to spin on its axis about several times a second, and they can spin up to over 40,000 times per minute. They will slow over time as they lose energy from that supernova explosion, but right when they form, they spin incredibly, incredibly fast. So they have a really high rotation speed and a really high density. So neutron stars are super dense. They are basically a giant ball of neutrons, one of the densest things in the universe. And it seems like it shouldn't be possible to get any denser than a neutron star is because there's already subatomic particles pressing in on each other. But it turns out that if there's enough mass in that original star and it's packed into a small enough volume, the collective pull of that gravity can crush even a neutron star, even something that's already that dense. So the mass of a neutron star cannot exceed about 3 solar masses, so 3 times the mass of our sun. And if it's more massive than that, then gravity is going to take over. Nothing's going to be able to stop that collapse. Nothing's going to be able to stop it from collapsing further. And it's going to become something called a black hole. So as the core becomes smaller and smaller, the gravitational pull inside in the vicinity of that black hole becomes so great that nothing, not even light, can escape it, and that gives it its name. Again, astronomers aren't super creative because we see no light from it. We just call it a hole in space, and it doesn't give off radiation, so it appears to us as black. So it's just this empty point in space because we can't receive any light from it. So that's all the information that we get from outer space. Comes from light, comes from all the different types of radiation in the electromagnetic spectrum that we studied last week. And if we can't receive any information from it, then we have a hard time determining what it is. And then we name it a black hole because we can't see anything. So black holes are going to be super interesting. We're going to get into the details of this a little bit further. But Newtonian mechanics, the tool that we've used up until now in order to study the universe, we talked about Newtonian motion in week 1. We talked about Newton's 3 laws of motion. In just a second, we're going to talk about Newton's universal law of gravitation. And these are great laws, and they work everywhere except for at extreme conditions, extreme places in the universe, and they actually break down the laws that Newton put forth that were accepted for so long, break down in the presence of super strong gravitational fields and near the speed of light. So those laws cannot adequately explain or describe the conditions there. So we have to use a more modern theory, something called relativity, which we're leading into in just a second. But we're going to use 2 parts of relativity. There's a general relativity, which describes gravity, and then special relativity, which describes motion. We'll talk about those in just a second. But we can still use some of the aspects of Newtonian mechanics in order to describe these extreme bodies. So if we consider the concept of escape speed, which is the speed that is needed to escape a gravitational force. Noreen, hold on one sec, I just saw your question. If light can't escape, then how is it a black hole? Wouldn't light be prominent? So black is the absence of all of light. So it's not the combination of any 2 different colors or anything like that, any 2 frequencies or anything like that. It's just it's the absence of all the different frequencies. So if you were inside a black hole and you tried to shine a light out of it, that light wouldn't be able to escape outside of the surface of that black hole. Does that make sense? Good question, though. Yeah, excellent. It's weird stuff. So definitely ask as many questions as you need. So we can look at the escape speed, which you can see the equation on screen there. The velocity needed to escape the gravitational pull of some object is equal to the square root of 2 times the gravitational constant, which is 6.67 times 10 to the negative 11. It's a physical constant, times the mass of the object divided by the radius of that object. So the escape speed on Earth is about 8,000 meters per second. 11,200 meters per second. 8,000 is what's needed to orbit. But in order to get away from the surface of the Earth, an object has to travel at about 11,200 meters per second. Otherwise, it will be pulled back down to the surface or be pulled into orbit. But if we wanted to travel elsewhere in our solar system, go to Mars, get out of our own little area in the solar system, then we would need to travel faster than 11,200. The escape speed of the sun is about 42,500 meters per second. So we would need to travel faster than that because the sun has a lot more mass in order to escape the gravitational pull of the sun, not be pulled back down to its surface or go into orbit around it. So for a black hole, this escape speed is greater than 300 million meters per second. So if you get inside the gravitational pull area of a black hole, then you can't escape, because we learned last week that the speed of light is the universal speed limit. So that's our point one here. Nothing can travel faster than the speed of light, so we don't have anything that can escape from a black hole. And then the second thing we're going to keep in mind is that all things, including light, are affected by gravity. All right, so a couple of properties of a black hole. We have the singularity, which is the point of infinite density at the center. And then the event horizon, which is considered to be the surface of a black hole, even though it doesn't really have a physical surface. And then extending out to the event horizon is something called the Schwarzschild radius. And this is the special name that we give the critical radius at which the escape speed from the black hole would equal the speed of light, and within which the object could no longer be seen. So we call this the Schwarzschild radius, which is my least favorite term to say in physics and astronomy, but it's named after a German astronomer named Karl Schwarzschild, and he was the one who first kind of studied the properties of it. So it's important to note that any object can become a black hole. It's the radius to which the object would have to be compressed with the amount of mass that it has in order to become a black hole. So that Schwarzschild radius is the radius to which an object would need to be compressed. So this, as you might guess, is proportional to its mass. So for Earth, if you took the entire mass of the Earth and started compressing it down further and further and further, in order for Earth's mass to become a black hole, you would need to compress it down to about a radius of 1 centimeter. For Jupiter has more mass, so it would need to be compressed down to about 3 meters. For the sun, it would be about 3,000 meters. And then for a star that's maybe 3 times larger than... Stop. Sorry, 1 second. All right, so for a star that is more massive than the sun, it would only need to be compressed down to a size that's larger than 3,000 meters. If we had a 3 solar mass star, then it would be about 9,000 meters across. So a convenient rule of thumb is that the Schwarzschild radius of an object is simply 3,000 meters multiplied by the object's mass and solar masses, if you ever needed to figure that out. But you could be compressed to a black hole, but you would just have to be compressed to a really, 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 really small radius. So any mass can become a black hole. It's just at the size that it's compressed to, and that size that it is compressed to is called the Schwarzschild radius. All right. So we're going to revisit black holes a little bit later once we go over relativity. But I want to do that first and then go back and see how black holes are affected by these new laws of relativity that we're going to introduce. So that leads us into our next topics, and these are going to be the last sections of your course notes. I believe it's 4 through 6, but we're going to talk about relativity. And first, Newton's universal law of gravitation, which is the building block for relativity that kind of breaks down in extreme conditions. And then we'll talk briefly about dark matter and energy, and then also the Big Bang and the fate of our universe. So first, before we say what Einstein fixed about Newton's laws, let's talk about Newton's law. So we've learned throughout this course, we've talked a lot about gravity. We've talked a lot about what causes gravity, some orbits, that kind of stuff. And we know that the force that keeps everything in place on the surface of the Earth is going to be gravity. What causes that force is going to be the mass of the Earth. So Earth has a gravitational pull due to its mass. So what Newton figured out and kind of expounded upon that statement is that, okay, everything's drawn towards the surface of the Earth because of its mass. We know that, but then wouldn't it make sense that anything that has mass would also have a gravitational pull? So this was Newton's big contribution to gravity. He had his laws of motion, and then his big contribution to gravity was not that he discovered gravity. That's a common misconception. A lot of times people think that because you see the picture of Newton with an apple falling on his head, they think that he discovered gravity. But Galileo, uh, who actually died in the same year that Isaac Newton was born, had discovered many, many years before that there was a constant acceleration pulling objects towards the surface of the Earth at the same rate, which he defined as gravity. So what Isaac Newton did is went beyond that statement and said that, okay, everything falls towards the surface of the Earth, but that gravitational force is not limited to the Earth. It is a universal concept. So he said, every object in the universe that has mass is going to be attracted to any other object that has mass as well. The more mass something has, the greater that gravitational pull, and the closer two objects are together, the greater that gravitational pull as well. The reason that we don't notice the gravitational pull from someone standing next to us is because the mass of the Earth is so large that it overcomes all the other gravitational forces between us. So that's the only one that we really notice. But if we were able to go out in space with no other gravitational forces around us, just floating out in the vacuum of space with you and a friend, those two masses would be attracted towards each other because we wouldn't have the Earth that's pulling us down, that's preventing us from feeling that. So there's an equation that goes along with this, and it's Newton's universal law of gravitation equation. And it might look familiar in format to the electrostatic force equation that we learned in week 3. But basically what it says is that the gravitational force is equal to the gravitational constant, which is a physical constant. It would be the same that same number every time you do this calculation, 6.67 times 10 to the negative 11. And then that constant is multiplied by the two masses. So anytime you're measuring the gravitational force between two masses, you multiply the mass of the first object times the mass of the second object, and then divided by the distance between the two masses squared. So we're not going to ask you to do this calculation this week. What we're mostly concerned with is the relationships in between these variables. And so we can see that gravitational force is going to be directly proportional to both of the masses. So what that means is that the greater the mass, the greater the gravitational force between those two objects when kept at the same distance away from each other. So two really massive objects like the Earth and the Moon are going to have a large gravitational force between them because they're very, very massive. But if we took Jupiter and put it in the same spot as the Moon is, then the gravitational force between those two would be greater because Jupiter has a lot more mass. So they're directly proportional to both of the masses. If you increase one, it increases the gravitational force. And then the gravitational force is inversely and exponentially proportional to distance. So that means that the farther you are away from an object, the less gravitational force between you. And it increases and decreases by an exponential amount. So if you get further away from a mass, then the gravitational force between you and that mass is going to decrease by an exponential amount. And this is a really important relationship. We saw it already in week 3, but it also applies to gravitational force, and that is the inverse square law. So gravitational forces follow the inverse square law because of the proportional relationship between gravitational force and distance. So a way to rewrite this just in terms of the inverse square law, because the inverse square law is really only concerned with the relationship between force and distance. We could just rewrite this and say the gravitational force is proportional to 1 over the distance squared. So let's take a look at what this does. If you watch the answers video for this week, I already went through this because someone asked about the inverse square law. But it's a really important concept, especially for a lot of the degree programs that we have here at Full Sail, because it relates to sound and light and electricity and magnetism. So can't hurt to go over it again. So the inverse square law. Let's take an unrealistic example of a giant apple floating out in space and being held a certain distance away from the Earth. So we can say that that apple is 1 unit of distance away from the Earth. It doesn't matter. We're not going to clarify as if it's a mile, a meter, or a kilometer, or anything like that. We're just saying it's 1 unit of distance away for the purposes of this example. If we took that apple and moved it 2 times further away, then that means that we would have increased our distance by a factor of 2. So the inverse square law tells us what happens to the gravitational force when we increase our distance by a factor of 2. And so there's 2 parts to it. There's the inverse part and there's the square part. When the distance increases, the force will decrease. Inverse means that the opposite thing is going to happen. So as one goes up, the other one goes down. So if distance increases by 2, then the force is going to decrease. And it's not just inversely proportional, it's also exponentially proportional. So that's the square part of the law. So if the distance increases by a factor of 2, that means that the force is going to decrease by a factor of 2 squared, or 4. So let's look at this again. Let's now say that we have our apple. We are originally at 1 unit of distance, and now we've moved it 3 times further away. So our distance has increased by a factor of 3. That means our force is going to decrease. It's going to do the opposite thing by a factor of 3 squared, or 9. So distance goes up by 3, force goes down by 9. And again, if we move it 4 times further away, exactly the same thing. Distance goes up by 4, the force goes down by a factor of 4 squared, or 16. And then, so you probably got that. You get further away, gravitational force is less. Let's move it closer and see the relationship. So now we're going to say that our original distance was 4 units away, 4 units of distance away. If we take that apple and we move it from 4 to 2, then that means that the object has gotten closer. So the distance is going to go down. And since we went from 4 to 2, it went down by a factor of 2. So distance decreases by 2. And this time, because we're moving closer, the force is going to increase by a factor of 2 squared, or 4. So it's still that relationship, regardless if you're moving closer or farther away. We still have the inverse, the opposite thing happens, and the amount that it goes up or down by is going to be by a factor of a square. Force increases by 2 squared equals 4. Yep. Any questions on that? All right. So this was Newton's big contribution. Newton had a ton of big contributions, but his theory of gravitation was relatively quickly accepted without a whole lot of question. And it remained unquestioned until about the beginning of the 1900s, so not even that long ago. Well, in in relative terms. But around the beginning of the 1900s, a guy named Albert Einstein came around, shook the foundation of Newtonian physics and physics in general, and introduced something called the special theory of relativity, which he introduced in 1905, and then something called the general theory of relativity, which addressed gravity, in 1915. So the special theory of relativity shows that Newton's 3 laws are his laws of motion, are only approximately correct, and they break down when you have extreme velocity. So when speeds approach the speed of light, then Newtonian mechanics, Newtonian motion, breaks down and can't explain it anymore. The general theory of relativity came around 10 years later, showed that Newton's law of gravitation that we just talked about is correct for most cases, but it breaks down in the presence of very strong gravitational fields, like when we talked about the black holes and neutron stars and getting really the really massive stuff, the things with the strongest gravitational pulls. So Newton's laws break down around that point. So Albert Einstein came up with these two laws. I just want to give a little shout out to Einstein. He's a fascinating man. If you're interested in biographies or anything like that, then he has a really good one. He has a very interesting life, and I just want to kind of just point out a couple of things that relate to this and things that I thought were interesting about the beginning of his life. So Einstein was born in Germany. And he's one of of course, if you say to half the people in the world, name a scientist, it's going to be Albert Einstein. And so he's one of the most influential physicists of all time. And you might have heard this before if you've ever heard about his childhood, but Einstein wasn't really considered to be a very bright child. He had a little bit of a speech difficulty where he talked slow, um, and he was really just they took that as a disability, but he was really just being careful about what he was saying, pausing to consider what he was going to say next. But because of this, his teachers talked to his family and they said, okay, he's a little bit slower. He's not getting the material as fast because he talks slow. So maybe you might want to hire a tutor. So his family hired a Polish medical student in order to tutor Einstein, which is crazy. But this man, his name was Max Talmud, and he kind of recognized that he wasn't really needed to tutor him, but he did introduce him to higher mathematics and philosophy. And one of the books that he shared with him was a children's science book where the author imagined riding alongside electricity that was traveling inside of a telegraph wire. And Einstein said that this was a marked moment in his life because he began to wonder what a light beam would look like if you could run alongside it at the same speed. So he said, well, if light were a wave, and this is kind of going back to the wave particle thing, if light were a wave, then if you're moving at the same speed of it alongside of it, then the light beam should appear as a frozen wave. It should look stationary. But in reality, the light beam is moving, of course. So this paradox led him to write his first scientific paper at age 16. And this question of the relative speed compared to stationary observers moving along with light was the question that would dominate his thinking for many years to come and led him to his approach in looking at relativity. So we're going to look at both special relativity and general relativity and look at the implications of both of those to science in general. I just wanted to share my favorite quote from Einstein, which is, "I have no special talent. I am only passionately curious," which I don't know if I necessarily agree with the fact that Einstein didn't have any special talents. I think he is beyond talented, but just keeping in mind that people who even feel like they're not talented like Einstein did, having that curiosity and maintaining that curiosity and just constantly asking questions and not letting just accepting things is really an important thing in life. So I just wanted to share that. My other favorite quote is that he came up with all his best ideas while riding his bicycle, which is why I included that picture. But all right. Yes, he is absolutely being humble, but I still like the idea of it. All right, so special relativity first. He came up with special relativity in 1905. This is his first part of relativity, and this has to do with the laws of motion. It's modifying Newton's laws of motions to include extreme speeds. So, three main parts to special relativity. And the first one is that the speed of light is the maximum possible speed, and it is always measured to have the same value by all observers. So with Newtonian mechanics, if you look at example A on the screen here, if you have a person in a car that is driving in that car and he shoots a gun outside of the window, and you have an outside observer that is measuring the speed of that bullet, that observer is going to measure the speed of the bullet plus the speed of the car. So even though the car is moving 100 kilometers per hour, the bullet's moving 1,000 kilometers per hour relative to the car, but since it was an outside observer, they're going to see that see that bullet moving at 1,100 kilometers per hour. This cannot happen with a light beam because, as we said, part one, the speed of light is the maximum possible speed, so we can't measure anything faster than that. So if you have a spaceship that is traveling at about a tenth of the speed of light, 0.1 c, and it shines a beam outside of the ship, the observer does not measure 1.1 c, which would be over 300 million meters per second, over the speed of light, because nothing can be measured faster than that. So the light beam does not have a velocity equal to the spaceship plus the beam. The observer still is going to see c, or 300 million meters per second, regardless of the speed of the ship. All right. Now, part two says there is no absolute frame of reference and no absolute state of rest. So what this means is that there's no preferred observer relative to whom all other velocities can be measured. So anytime we measure a velocity, it's a relative velocity between different states of motion. So we measure a lot of speeds and stuff compared to where we are on Earth, and assume, just say, okay, we're stationary, everything else is moving relative to us. But we're not, a lot of times we're not taking into account the fact that we're moving all the time when we stand on the surface of the Earth. So if you stand still on the surface of the Earth, you might feel like you're standing still, but you're actually moving a lot through space. So when you stand still on the surface of the Earth, you are rotating with the surface of the Earth. The Earth rotates at a speed of over 1,000 miles per hour. It also revolves, it orbits around the sun at a speed of about 67,000 miles per hour. And then the solar system itself, the sun and all the planets orbit around the center of the Milky Way galaxy at a speed of about 500,000 miles per hour. And then the speed of the galaxy through space is moving about 2 million miles per hour. So add all those things together, you're standing still on the surface of the Earth, you're moving about 3 million miles per hour. So if we measure a velocity, then that speed is being measured relative to the 3 million miles per hour that we're moving standing still on the surface of the Earth. And that would be the same anywhere else in the universe. So there's no absolute place where we can measure all speeds, no absolute state of rest. All right, and then part three is going to be that space and time are not independent anymore, but they can instead be identified as as components of a single entity, which we will now call space-time. So just like there's no absolute universal frame of reference, there's also no absolute universal time. This is where we get into time dilation and how observers' clocks are going to tick at different rates depending on the observer's motion relative to each other. So we're going to do a couple of thought experiments here because we can't really do actual experiments with this, but at least not online. But So special relativity is going to be equivalent to Newtonian mechanics when describing objects that move much more slowly than the speed of light, but it's going to differ greatly at approaching the speed of light, or something we call relativistic speeds. So let's do a thought experiment to look at some of these components. So we have Sally standing in a field, and John is riding in a railroad car that is moving with velocity v. John shines a flashlight in the direction in which he is moving. What's going to happen? Let's see. Noreen, space and time are one and the same. Yes, they are they're components of a single entity, which is space-time. So we're going to consider them the same and say that they're all going to be affected by relative motion and also by gravity as well. They're going to be affected in the same way, in a sense. Great question. All right, so if we have John shine a flashlight in the direction in which he is moving, what's going to happen? So we learned this from the part 1 of the experiment because of the principle of the constancy of the velocity of light, meaning that light is never going to be measured moving faster than the speed of light. Then each observer, both Sally and John, if they measured the speed of light, even though John's moving and Sally's sitting still, that they're both going to measure the light beam from the flashlight as traveling at the same speed. All right, so that one's not super exciting. Thought experiment number 2. Sally's standing in a field. Next to her, we have a light clock. A light clock is going to be 2 mirrors that are reflecting a beam of light back and forth, and then the journey, one cycle from one mirror back to the other one again, counts as 1 tick of the clock. So we're used to 1 tick of the clock being a second, so we can just define it as that. Obviously, light is going to move a lot faster than that, but we'll just say that as the light beam goes up once and then down once, that's 1 tick of the clock, that's 1 second. So the light clocks are going to be synchronized with each other. Sally and John are going to be wearing watches that are synchronized to their light clocks as well. So John is standing on a stationary railroad car. He also has a light clock, and his clock is synchronized with Sally's and his own wristwatch. So what happens here? Again, this is kind of just building up to the interesting one. Nothing unusual is going to happen here because no one's moving. They're stationary relative to each other. So John's watch, Sally's watch, they're going to stay perfectly synchronized with each other and then also synchronized with their light clock. But now, let's make it interesting. Thought experiment number 3. We now have the exact same setup, except for now the railroad car that John is standing on is moving to the left with a velocity v. So what's going to happen? From John's perspective, the beam of light keeps going up and down between the mirrors. But from Sally's perspective, the light now has to travel a diagonal path from one mirror to another. So since Sally still measures the speed of light as c, remember they're both going to measure the speed of light the same, she's now going to observe John's light clock as ticking slower than hers because the light now has a longer distance to travel. But since John still experiences his watch as being synchronized with his clock, Sally's going to see his watch slow down along with his clock. So for John, if he looks to his left and sees that light clock going up and down, it's going to look like it's doing the same thing for him because he's moving along with it. But for Sally, she observes that light having to go a longer distance, but since the speed is going to be the same, for both of them, that's going to affect the amount of time that it takes for that each of them observe. So just to use some random numbers, we just say, well, we'll use the speed of light. They're both going to measure the speed of light to be 300 million meters per second. And then let's say that we have let's say that the distance from one mirror to the other in the light clock is 1 meter. So one full trip would be that it travels 2 meters. So that's going to be what changes. John's going to see it just go up and down once, but Sally's going to see it go diagonal, which means that it's going to have to cover a longer distance from her perspective because that car is in motion. So if you calculate the amount of time that it took for the light clock to tick once, then John's going to measure it as one, Sally's going to measure it as another, but because their watches are still synchronized, they're still going to measure the time to be the same. So John's watch is actually going to slow down. So if John got off that railroad car and compared his watch to Sally's, they would no longer be synchronized because time actually slows down with a moving object. And that is time dilation. So I'm actually not going to get a whole lot into these other ones. The effects of special relativity, time dilation. We also have length contraction, relativistic Doppler effect, and relativistic mass. Let's look a little closer at time dilation. So you might have heard before of something called the twin paradox. And this is going to be the effects of special relativity when moving at relativistic speeds. So if you had two twins that were both on the surface of the Earth, obviously they're about the exact same age, and you take one of the twins and then send them out into space, moving at relativistic speeds for an extended period of time, then time would slow down for them because they're moving at relativistic speeds and light slows down at relativistic speeds. So time slows down for relativistic speeds. So that object, that person inside of the spaceship moving at relativistic speeds isn't going to notice anything different. They're still going to think, okay, time's moving the same, time's moving the same. But when they come back to the surface of the Earth, then more time would have passed on Earth because it was stationary. So the twin that was on Earth might have aged 30 years, whereas the guy in the spaceship might have only aged 10 years. So the aging process would actually be different as well, which would show that the time actually changes. All right, so there is a calculation for this. T prime, the dilated time, equals the time divided by the square root of 1 minus v squared over c squared. So just to show you, moving at slower speeds, not really that close to the speed of light, isn't going to have a whole lot of an effect on the time. Still, it happens, but it happens to a small degree that's not super important or drastic or measurable. So moving at only 10% the speed of light, if we do this calculation, then we would see that the difference between the observed time and the observer's time and the object in motion's time is only about 1.005 difference. But if we speed up and if we move at closer to the speed of light, say 95% the speed of light, then the difference in the times goes up to almost to greater than a factor of 3. So that would be like our twin example. If we sent a twin away, they travel for 10 years through space, and they would come back down, and the observer's time would be about 3.2 times longer than what the guy moving had observed. They would have aged 30 years. You might have only aged 10 years moving at relativistic speeds. All right. Any questions on that? I know it's a lot to take in. All right, you got it. All right, so another effect I'm just going to briefly mention, another aspect of Einstein's theory of special relativity is length contraction. And that means that the length of objects undergoes a contraction along the dimension of motion when moving at relativistic speeds. So an observer at rest relative to the moving object would observe the moving object to be shorter in length than it actually is. So an object at rest might be measured to be, let's say, 200 feet long, but when the same object is moving at relativistic speeds relative to the observer, they would have a measured length that is less and maybe much less than 200 feet. So this phenomena, like the time dilation, is not due to errors in measurements or faulty observations when things go faster. The object is actually contracted in length as seen from the stationary reference frame. So the amount of contraction is dependent upon the object's speed relative to the observer. So it's more drastic the closer that you get to the speed of light. And it's actually only significant at all when you get to relativistic speeds. All right, so that's special relativity. When constructing special relativity, Einstein ran into a problem. And his problem was taking Newton's other great contribution, which was Newton's universal law of gravitation, and putting that into the framework of relativity. It was a much more complex mathematical problem, and that's why it took Einstein another 10 years to come up with. So the problem is that special relativity is only valid for systems that are not accelerating. So since from Newton's second law, we know that acceleration implies a force, that means that special relativity is valid only when no forces are acting on the object. So anytime there's a gravitational field present, this wouldn't be valid, which is not very realistic because there's usually a gravitational field present. So the general theory of relativity was Einstein's modification and tremendous effort to remove that restriction on special relativity. So another thought experiment that he had was to imagine that to try to figure this out was to imagine that you're enclosed in an elevator with no windows so that you can't directly observe the outside world. And then we take that elevator and we place it out in space. If you place it out in space, you're weightless. So you're floating out in this elevator, you in the elevator, you're both weightless, you don't feel the ground against your feet. But imagine that all of a sudden you begin to feel the floor press up against your feet, so weight has apparently returned. A couple of things could have happened that could have caused this. A large mass could have come by and you're feeling the downward acceleration, or the elevator also could have begun to accelerate upward for some reason. There's no experiment that you could do inside of that elevator without looking outside, without being able to see which direction you were going, that would tell you, that would distinguish between these two possibilities. So Einstein said, since there's no way to tell the difference between a gravitational field and an accelerated frame of reference in something that he called the equivalence principle, he succeeded in addressing gravity as just an acceleration of particles. So that might not sound super significant, but it was very important to the mathematical relationships that he came up with in order to be able to address this in that specific way. An easier way to say this is that to include this new part, space-time, that quantity that we just discussed, space-time needs to be curved. So the central concept, the main concept of general relativity, is that all matter, anything that has mass, tends to warp or curve space around it in its vicinity. So the more massive the object, the greater it warps space. And then objects that have mass, such as planets and stars, react to this warping by changing their paths. So one of the best ways I've heard this general relativity just put into a single sentence, this is from a podcast I listened to with Neil deGrasse Tyson, and he said, matter tells space how to curve, and space tells matter how to move. So in the Newtonian view of gravity, particles and objects moved on these curved paths because they were acted upon by some gravitational force for some reason. For some reason, masses attracted each other, and we didn't really know why. We couldn't really explain why, but we just knew that they attracted each other. We say, okay, there must be some force between them. But with Einstein's relativity, those same particles are now moving on those curved paths because they're simply just falling freely through space with their own inertia, and then they follow the curvature of space-time that's produced by a massive nearby object. So this was seen, and why we say this Newton's law breaks down is because we saw we've actually witnessed that light is bent around really massive objects. So with Newton's universal law of gravitation, that wouldn't work. Light should not be affected by gravity if Newton's universal law of gravitation was absolutely and universally correct, because light has no mass. It's a massless particle. So Newton's universal law of gravitation said that the gravitational force equals the gravitational constant times mass 1 times mass 2 divided by the distance squared. If one of those masses is 0, then that would make the whole calculation gravitational force equals 0. So it shouldn't affect it. But we've witnessed during a solar eclipse, mostly, usually the sun's light blocks out so much of the light behind it that we can't see any of it. But during a solar eclipse, a lot of that light is blocked out, and we can see light from distant stars and other celestial objects coming from behind the sun during an eclipse. And what we witnessed is that light actually bent around around the sun. So what general relativity says is now that light is just following the path, the curvature of space-time, and it's traveling in a straight line as much as it can, but when space is warped, it curves around in the same way. So it's traveling as straight as it can, but still matching the curvature of space-time. All right, so the more massive an object, the greater the warping. So to fit black holes into this is saying, okay, so the sun is really massive, it warps space-time. The gravitational pull is stronger, would be the way that we had said it before. Now we say the sun warps space-time. A neutron star has a greater gravitational pull, so it warps space-time to a greater extent. And with a black hole, when that hole becomes infinitely deep, so much so that nothing, even light, can escape, then we call it a black hole. So with it warps space, but these things, these really massive objects, also warp time as well. Remember, space and time are now one single entity known as space-time. If you're able to travel near a black hole without getting sucked in, time will actually slow down for you there as well. So time warps in really strong gravitational fields as well as the space around it. All right. So that's general relativity. Do you have any questions on that? Does that make sense for the most part? Okay, great. All right, so just a few more topics, and I'll let you go for the day. Dark matter. We have we have a lot of things that we don't understand about the universe. One of my favorite things, one of the reasons I went into studying astrophysics, is because of how much we don't know. We don't understand upwards of 96% of what the universe is, and a lot of the stuff that we name is just doing that. We don't know what it is, we can't really explain it, but we give it a name because we know that it's there. So two of these things are that we've given names to that we don't fully understand are going to be dark matter and dark energy. So dark matter is a recently discovered new state of matter that surrounds galaxies and is not yet well understood. And the reason that it's not well understood is because first of all, we don't see it, which is why we call it dark matter, and it doesn't interact with radiation or electromagnetic waves in any normal way. So it can't be seen, it can't be touched. If light passes through it without interacting with it, and all of the information that we get from space comes from most of the information we get from space. We can't actually go out, we can't actually travel out into space. So all the information we receive comes from that radiation across a lot of different frequencies and wavelengths of the electromagnetic spectrum. But if there's no interaction with light that's passing through this material and it's not giving off any of its own electromagnetic radiation, then we can't really obtain any information about it. So how do we know it exists at all if we can't see it or touch it? Well, the answer is that we see what it does. We see the effects of it. We see the gravity, the way that the gravity of this dark matter has affected objects that we can see around it. So we learned that masses, the gravitational force between masses, um, increases the closer you get to each other. So this says that if you look at the Milky Way galaxy, the densest part of the Milky Way galaxy is the center of it. There's actually a supermassive black hole at the center of our Milky Way galaxy. So there's the most mass at the center of the galaxy, just like there's the most mass at the center of our solar system. As you get further and further away from the center of that, the massive center, the orbital speed should go down. It should decrease in speed because you're getting further and further away from that most mass. And if you look at our solar system, the fastest orbital speeds are the ones that are closest to the sun. So Mercury travels the fastest, then Venus, and then Earth, and then as you get further and further away, it takes longer and longer to go around. Also, you're traveling at a greater distance. But the stars, when this was calculated, the stars at the edge of the galaxies were actually traveling faster than they should have been if all the mass was contained inside of the visible light, the visible part of the galaxy. So we had to conclude that there's some gravity from invisible matter at the outer edge of the galaxies that is accelerating the outer stars. So we can see the gravitational effects of this mass, we just can't see it through electromagnetic radiation. And there is something, it's called the dark halo, that extends around our galaxy, and it gives our galaxy a lot more mass than what we can actually see. So there's the bright part of the galaxy, and then we can see that there's also more mass, that we've calculated more mass for the entire galaxy than what is visible. So we don't know what it is. We don't know why it's there. We don't know what it's made up of. So we just call it dark matter. And then dark energy is a recently discovered state of energy that exists in empty space and again is not yet well understood. So it was recently discovered that the universe is expanding, and that's fine. We might say, okay, well, the Big Bang happened, everything started in the center, and then it expanded out in all directions. So that's fine, but what you would if that was it, if that was all the forces that were driving the acceleration, or so driving the expansion of the universe, then eventually that should slow down, because the big bang isn't happening anymore, so that energy is going to dissipate eventually, and matter should take over. Masses and gravitational forces should take over. So one of the theories for the fate of the universe was that it was going to expand for a while, but then once the energy from that original expansion from the Big Bang dissipated, then the gravitational forces of all the mass in the universe would eventually start pulling everything back together. But we've recently measured the relative speeds between galaxies, measured the speed of the space in between galaxies, and we found out that it's actually accelerating. So the universe is not only expanding, but the rate of expansion is accelerating. And that would only make sense if there was some other force, some other energy that is driving that acceleration. We don't know what that is, but it doesn't seem to be slowing down at all. And it seems to be increasing at a steady acceleration. And so we just name that energy dark energy. So the current most accepted theory of the universe is that it's going to continue to expand forever because there's no end in sight for this dark energy, um, to go away. There's no reason why we think it would go away. But we don't understand why it's there. We don't understand where it came from. We don't understand what makes that energy persist, that continues that acceleration. So again, we don't understand it, so we just give a name to it, dark energy. And then lastly, kind of just mentioned this, but this is the the most widely accepted model for the formation of the universe. And that's the Big Bang model. It states that all matter, all energy erupted from an infinitesimal point or a singularity and expanded into its current state. So that expansion was the original thing that caused the universe, and now the dark energy is driving that expansion even further. So the speculation for the fate of the universe is to continue expanding forever without halting. Now, of course, there's a lot of questions that go along with this. So if it started from a singularity, if it started from a point, infinitesimal point of infinite density, then where did that come from? What was before that? What is it expanding into? Is there something that it's pressing into? Is it pressing into another universe in a different place? There's so many questions that stem from these topics, and that's why I think that astronomy and cosmology and astrophysics is so fascinating, because we have all these questions that people are seeking to find, but we do not yet have the answers for. All right, so that is all I have. Noreen, if gravity is a constant, how will it expand with the dark energy? So yeah, so gravity is a constant, and gravitational forces, um, pull inward. So it's opposing dark energy. But right now, it's showing that the dark energy is stronger than the gravitational forces because it's accelerating those objects away from each other. And we just learned that the farther two objects are from each other, the lesser the gravitational force between them. So as those objects are being pulled farther and farther apart, the gravity between them is getting less and less. And it's showing that the space is actually expanding between them. Those objects aren't actually just moving away from each other in a finite space. The space between those two objects is actually expanding. So the universe is getting larger. Does that make sense? Right. So gravity, the force itself isn't changing, but the distance between those two objects is changing. So it just changes our calculation. Great question. All right. Do you have any questions on anything else? All right. Well, thank you for coming this morning. I appreciate it, and appreciate all your great questions. And like I said, I will. I don't know if I said this while I was recording or not, but I will put out one more lecture this week, on quantum mechanics. I went a little bit out of order, but I will go over the quantum stuff in another lecture that I will post in the go-to training and course notes activity for week 4. But I hope you guys are enjoying this week. It's kind of more of a conceptual, fun week, thinking about the really, really small and the really, really large stuff in the universe. And if you have any questions, just as always, let me know. Thank you guys.